Welcome back to Columbia Physics Preceptor Television. Today I will be giving an example introduction for the specific heat experiment. So today we will be doing an experiment which measures the specific heat of materials and looks at the mechanical equivalence of heat. Now you might ask yourself, what is heat? It's a common misconception that heat and temperature are sort of the same thing. But in the physical realm, heat and temperature are actually different but related things. We can think of heat as the amount of thermal energy that a system has or that can be transferred from one system to another. Temperature, or the temperature of a body, is an approximate measure of how much heat that body has. However, there are some numerical factors, such as the specific heat and the mass of the body, that enter into the equation as well. We can say that in order for a temperature to rise in in order for a body to rise in temperature, it has to have heat added to it. Not all materials rise in temperature the same way. Due to differences in their microscopic structure, some materials may require more heat to rise by 1 degree centigrade. But we can relate these quantities together. Say we have a mass m, which goes through a temperature change delta T, where this is the difference between the final temperature and the initial temperature. We can say that this delta T is equal to the heat that has been added to the system divided by the mass of the body times its specific heat, C. We can rewrite this to simply give the heat responsible for that temperature change is equal to the change in temperature times the mass times the specific heat. What we would like to do is measure the specific heat of lead. To do this, we'll have a body of water sitting inside a styrofoam container to try to insulate it from the outside world. This will minimize the amount of errant heat which may enter or exit the system simply from the ambient air. You'll heat up the lead to a temperature of approximately 100 degrees Celsius. The lead will have lots of heat, so that when we put it into a cool bath of water, the heat from the lead will try to escape, or will escape, into the water until the temperature of the lead and the temperature of the water are equal at an equilibrium temperature, TE. We can equate how much heat has been transferred by using two equations. The first will be the amount of heat lost by the lead. This will be simply the mass of the lead times its specific heat times the temperature difference, where TL is the initial temperature of the lead and TE is the equilibrium temperature. The heat gained by the water will simply be the mass of the water times the water's own specific heat times the temperature change, where TW is the initial temperature of the water. We can relate these two by saying that heat must be conserved in this isolated system, so that the sum of the heat lost by the lead and the heat gained by the water has to sum to 0. This means that no heat has entered or exited from other sources. However, it should be noted that heat as a natural quantity always wants to go from warm to cold. So in this case, if our system here has any deviations from room temperature, heat from the ambient air will want to enter into the system or exit it. This will add uncertainties into your experiment. You will want to estimate these based on just a general knowledge of the differences in temperature of this system versus the ambient air and how quickly you think heat is transferred between the two. The second part of this experiment will be examining the mechanical equivalence of heat. We know that heat is a thermal form of energy, that is, energy which has simply been given to the molecules of a substance and allows them to vibrate around on a microscopic level. What we can do is see how mechanical energy such as gravitational or kinetic energy, is converted into this thermal energy. The numerical factor, a numerical factor relating the two quantities is known as the mechanical equivalence of heat. To do this, we will examine a system with a tube full of lead shot falling through a height h. When the lead shot reaches the bottom of the tube, what was once a gravitational potential energy, mgh, as it's falling becomes a kinetic energy, 1/2 mv squared. But when the lead lands at the bottom of the tube, all that energy is turned into either sound, a type of vibrational energy, or heat, vibration in the molecules of the system. By taking this tube of lead and inverting it a certain number of times, call it n times, we can take a measurable amount of gravitational potential energy and see how it is turned into heat by observing the temperature change of the lead shot inside the tube. To do this, you'll start by cooling down the lead slightly in a bath of ice water. Then, after reading the temperature off of a thermometer on the tube, you will invert the tube n times, where n should be about 75. And after those 75 inversions, you should read the temperature again and see how much heat has been added to that lead. This should give you a result where the total potential energy that the lead has had over the set of inversions becomes a numerical factor J times an amount of heat that has been added to the lead. Again, this J is the mechanical equivalence of heat. From the equation that we used last time, this Q can be rewritten as the mass of the lead times its specific heat times the change in temperature. You will measure the change in temperature. For the specific heat of the lead, you can either use the value that you found in the previous experiment, or you can use the numerically accepted value. Again, in taking into account uncertainties in this experiment, you should remember that heat will want to flow from hot to cold. So as your tube is slightly below room temperature, heat from the room will want to get into it. Also, as the lead heats up to slightly above room temperature, heat will want to escape the tube. You can presume that the tube is a good insulator. Cardboard tends to be a good insulator. But in this case, it's still a source of uncertainty for your measurements. Also, there may be other factors that introduce energy into the buckshot if it is not a perfect falling situation. You should try to estimate numerically the magnitude of these uncertainties. Also, you should remember when reading the thermometer on the tube, you should make sure that the buckshot is around the thermometer. Simply reading the thermometer from above while the lead shot is at the bottom will not be truly taking the temperature of the lead shot. That's all. Have fun.